For millennia, humanity has gazed skyward, dreaming of flight, of breaking the bonds of gravity that tether us to the earth. From the mythical wings of Icarus to the fantastical contraptions of Leonardo da Vinci, the desire to ascend has driven our imagination and our innovation. Today, that ancient dream takes two extraordinary forms: the colossal power of rockets, propelling us to the stars, and the exhilarating promise of jetpacks, offering personal flight. But how do these incredible machines truly work? What is the fundamental science that allows us to defy the very force that holds us down? This is the story of that science, a journey into the physics of propulsion, and the relentless human spirit that seeks to touch the sky. At the heart of every rocket launch and every jetpack flight lies a principle so elegant, yet so powerful. It underpins all of modern propulsion: Isaac Newton's third law of motion. It states that for every action, there is an equal and opposite reaction. Imagine a balloon. When you inflate it and let it go, the air rushes out in one direction, and the balloon shoots off in the opposite direction. This isn't magic, it's physics. The escaping air is the action, and the balloon's movement is the reaction. In a rocket or a jetpack, the principle is identical, just on a far grander and more controlled scale. Instead of air, these machines expel a high-velocity stream of exhaust gases or water downwards or backwards. This expulsion of mass in one direction creates an equal and opposite force, or thrust, pushing the vehicle and its occupants in the desired direction. It's a continuous, powerful push, earning potential energy into kinetic energy, and turning dreams into reality. Rockets are the titans of propulsion, designed to break free from Earth's gravity and journey into the vacuum of space. Their immense power comes from the controlled, explosive combustion of propellants. At its core, a rocket engine is a sophisticated chamber where fuel and an oxidizer are introduced, ignited, and rapidly burned. This combustion generates extremely hot, high-pressure gases. These gases are then directed through a specially shaped nozzle which accelerates them to supersonic speeds. The faster these gases are expelled, the greater the thrust generated, pushing the rocket skyward. Rocket propellants come in various forms. Liquid propellants, like liquid hydrogen and liquid oxygen, are highly efficient and allow for thrust control, making them ideal for complex maneuvers and long-duration burns. Solid propellants, on the other hand, are simpler to store and deploy, offering high thrust for shorter durations, often used in booster stages. Each type presents unique engineering challenges, from cryogenic storage for liquids to managing the intense heat and pressure of solid runs. To reach orbit, rockets also employ a technique called staging. As a rocket ascends, it burns through massive amounts of fuel. By shedding empty fuel tanks and engines a stage, the rocket becomes lighter, requiring less thrust to accelerate the remaining mass. This multi-stage approach is crucial for achieving the incredible velocities needed to escape Earth's gravitational pull and enter orbit, or even journey to other planets. While rockets conquer the cosmos, jetpacks aim for a more intimate form of flight: personal aerial mobility. The dream of strapping on a device and flying like a bird has captivated inventors for decades, leading to fascinating, albeit challenging, engineering solutions. One of the earliest successful jetpacks was the Bell rocket belt of the 1960s. This marvel used high-concentrated hydrogen peroxide, which when passed over a silver catalyst screen, rapidly set into superheated steam and oxygen. This powerful steam was then directed through nozzles to create thrust. While undeniably impressive, its flight time was agonizingly short, mere seconds, due to the rapid consumption of its specialized fuel. Modern jetpacks, like those developed by Jetman or Gravity Industries, often employ miniature turbojet engines, similar to those found on aircraft, but scaled down dramatically. These compact engines ingest air, compress it, mix it with fuel, ignite it, and expel hot exhaust gases. The pilot wears multiple such engines, often on their back and arms, allowing for distributed thrust and enhanced control. The challenges for jetpacks are immense. Fuel capacity remains a significant hurdle. Achieving practical flight durations without carrying an impractically large fuel tank is a constant engineering battle. Safety, stability, noise, and heat management are also critical considerations. The goal is not just to lift a person, but to do so safely, controllably, and for a reasonable period, moving personnel flight from a spectacle to a viable mode of transport. Generating thrust is only half the battle. Controlling it is equally, if not more, complex. Both rockets and jetpacks require sophisticated systems to maintain stability, direct their flight path, and respond to the pilot's or mission's commands. For rockets, control is primarily achieved through thrust vectoring. The nozzles of rocket engines are often gimbaled, meaning they can pivot slightly. By subtly changing the direction of the exhaust plume, even by a few degrees, the direction of the thrust can be altered, steering the massive vehicle through the atmosphere and into space. Onboard flight computers continuously monitor the rocket's attitude and trajectory, making thousands of adjustments per second to keep it on course. Jetpacks present a unique control challenge because the pilot is an integral part of the system. In multi-engine jet suits, the pilot uses hand controls to adjust the thrust of individual engines, creating differential forces that allow for turns, climbs, and descents. Body movements, much like a bird or a swimmer, also play a crucial role in maintaining balance and directing flight. Sophisticated sensors, gyroscopes, and accelerometers feed data to onboard computers, providing stability assistance and making split-second corrections to the engine thrust, helping the pilot maintain control in a dynamic three-dimensional environment. The interplay between raw power and precise control is what truly defines the success of these flying machines. Without it, the dream of flight would remain an uncontrollable, dangerous spectacle. The science of jetpacks and rockets is far from static. It is a field of relentless innovation, constantly pushing the boundaries of what's possible. The future promises advancements that will transform our relationship with the sky and beyond. For rockets, the focus is increasingly on reusability, pioneered by companies like SpaceX. By landing and reusing booster stages, the cost of space travel is dramatically reduced, opening up possibilities for more frequent launches, space tourism, and ambitious missions to the Moon and Mars. Advanced propulsion systems like electric ion thrusters or even theoretical nuclear propulsion promise to make interplanetary travel faster and more efficient. The future of jetpacks envisions more practical, longer-duration personal full flight. Research into more energy-dense fuels, quieter electric ducted fans, and advanced battery technologies could make personal-air vehicles a reality. Imagine a world where short-distance commutes are made through the air, or where emergency responders can reach inaccessible areas with unprecedented speed. Military and rescue applications are already being explored, demonstrating the incredible potential for these devices to augment human capability. Whether it's humanity's grand exodus into the cosmos or the exhilarating freedom of personal flight, the underlying science continues to evolve, bringing us closer to a future where the sky is no longer a limit, but a highway. From the fiery ascent of a rocket tearing through the atmosphere to the elegant ballad of a person soaring with a jetpack, we witness humanity's enduring quest to conquer gravity. It is a testament to our ingenuity, our curiosity, and our unyielding desire to explore. The science that underpins these marvels, Newton's elegant laws, the chemistry of propulsion, the precision of control systems, reminds us that the most profound dreams are often realized through the most fundamental understanding of our universe. As we continue to innovate, to refine, and to dream, one thing remains clear: the sky is not the limit, but merely the beginning. And with every new discovery, every new launch, every new flight, we rewrite the story of what it means to be human, reaching ever higher, ever further, into the boundless expanse of possibility. Thank you for watching our video. Don't forget to like and subscribe. We value your thoughts greatly. Let us know in the comments.